Good morning, everybody. Welcome to CHM 121. Dr. Khadija Abu Wahab, I will be taking you through the journey of gases. So, just a minute, I want to start this so that we can start. So, under this topic, we shall be looking at the kinetic theory of gases, the gas laws, the equation of the combined gas laws, the numerical values of R, and so in subsequent classes, we'll be progressing to other gas laws, and then eventually we'll now talk about deviation from the ideal gas law. Just like I said earlier, I'm Dr. Abdul Wahab, one of the chemistry lecturers that will be taking you CHM 121. So let's just try to refreshing our memory what we already know about gases. The physical properties of gas are independent of its chemical identity. And we shall see in a minute why that is so. Gas behavior is very different from the solid or the liquid that we see around us, and they have lower densities than solids and liquids. They don't have a shape of their own. They assume the volume and shape of their containers. And they are very, very compressible. They are the most compressible out of the three states of matters. And when you put gases together, the mixture of gases, irrespective of the identity of the gas, they mix evenly and completely in the container that you put them. And one of the features or characteristics of gases is that they exert pressure. What do you mean by pressure? Pressure is the force that is exerted over a surface area. If we want to use the ladies that wears the high heel as an example, she's doing that, she's exerting a pressure on the surface where she's walking. So imagine this as our column of air, and at the sea level, we'll have our 1 atmosphere. But as we now move high up, we'll see that the pressure decreases as we move above the sea level. As we go high up, pressure decreases. And this is just to emphasize something here before we move. This is the reason why, if you have ever been in an aircraft and the air hostess, when they are talking about in case there is a pressure drop, that will only happen because the aircraft is far above, it's very high up, and the higher we go, the lower the pressure. And so that is why there will be nose mask, the mask, the air mask available in the aircraft when we are traveling. Another instance that we can use to explain this is when we are in the lift, and the lift is going up. You'll be feeling that kind of emptiness. That's why some people, when they first come out of the lift, they feel that dizziness. It's because as we go high up, the available pressure is low, and then the air we can breathe in is also affected. Now, we have our barometer. That is the instrument that we use to measure the atmospheric pressure. But if we are generating the gas in the lab, we use manometer to measure the pressure of gas samples. And that is an example of how the manometer works. Now, this pressure we are talking about, what are the units of pressure? We have different units of pressure, and we can convert from one unit to another. We have torr, we have millimeter mercury, we have Pascal. Pascal is the SI unit, that is the Newton per meter square. It's named after the scientists. And then we have standard condition for gases, which is at 1 atmosphere and 0 degrees Celsius. So if this standard condition is met, it means that the gas, a mole of that gas under this standard condition, we occupy 22.4 dm or 22.4 liters. So under standard conditions, which is 1 atmosphere and 0 degrees Celsius, we have a mole of gas occupying 22.4 dm cube or 22.4 liters. A dm cube is actually the same thing as a liter. And these are the units, the interconvertible factor, or the converting factor from one unit of pressure to another. So these are 4 different units of pressure. We have atmosphere, we have millimeter mercury, we have torr, and then we have Pascal. So 1 atmosphere is the same thing as 760 millimeter mercury, which is the same thing as 760 torr, or 101.325 kilopascal. If we just quickly take an example of it's a simple math, but just refreshing our memory. And then we should bear in mind that this value, 101.325 kilopascal, that kilo, we already know in mathematics, kilo is multiplied by as in a factor of 1,000. So it means we are taking that kilopascal to pascal, we multiply by 1,000. That's why we have 101.325 pascal equals to 1,000 pascal equals to 1 kilopascal. If we have an example here, how many kilopascal is 1.37 atmosphere? All we just need to do is to convert. We have 1.37 atmosphere, and then we know 1 atmosphere is the same thing as 101.325, and then we divide by that to have our kilopascal. Here is another example. How many millimeter mercury is 231.5 kilopascal? There's a relationship between millimeter mercury and kilopascal. 760 millimeter mercury equals 101.325. So if we convert by dividing 760 by that value, then we have our value in millimeter mercury. Now, we need to know a little about the postulates Of course, it's something we are familiar with, but let's just try to refreshing our memory about what the kinetic molecular theory postulates. The first one is that gas consists of large number of molecules. It could be atoms, and they are usually separated by distances. The gases are very, very small. The particles are small. And also the volume of each particle is so small, such that we assume that they have negligible volume. That's the first postulate. The second one is that gas molecules are neither attractive, gas molecule exert neither attractive or nor repulsive forces on one another. That is, there is no force between the particles except when they collide. So the only way of interaction is that collision. And gas particles are in constant rapid straight line motion, moving in random directions. Gas particles collide with each other and with the containers, the wall of their containers, and this collision is perfectly elastic. What do we mean by perfectly elastic? It means that we have no loss of kinetic energy. That is, you just transfer law of conservation of energy, takes place there. And then the fifth one is about the kinetic energy, the average kinetic energy, or which measures the speed of the gas particles, is proportional to the Kelvin temperature of the gas. So, meaning that if you have two gases and they are at the same temperature, they will have the same average kinetic energy and be able to move at the same speed. That's what the fifth one is trying to say. And just to also remind us, the Kelvin, one of the great scientists that made this us possible to be teaching you. Those are the scientists that laid the foundation for this chemistry, for this the study of gases in chemistry. We have a unit, the SI unit for temperature is Kelvin. And then there's a relationship between the Kelvin and the usual degrees Celsius that we are familiar with. So if you want to convert from from degrees Celsius to Kelvin, you add 273 to the value of Celsius to convert to Kelvin. Now, if we have a sample of gas, and we already said these gases, they bump into each other. Some move fast, some move slowly, but there is an average speed. Now, if we look at this graph, it shows us the relative number of molecules with a particular speed as against the temperature. When you look at the first one, that is at 273 Kelvin, and then you look at the next one at 1273 Kelvin, and then you look at the third one, which is at 2273. You realize that the one that is labeled 273 Kelvin, the number of the speed, on the y-axis, you have the relative number of molecules with speed u, and then on the x-axis, you have the speed. As we increase the temperature, you see that the graph moves, as in the curves become wider. And then at a higher temperature, at 2273 Kelvin, is even more wider than the first one. The back, I usually like to describe this as like the back of a cheetah. You know, cheetah, one of the fastest animal that we know. When he wants to run, or when he's taking the speed, you know, that leap, when he's taking that leap, you know, that shape looks like that of that 2273 Kelvin, showing us that this is just trying to show us that as we increase the temperature, the speed increases and the relative number of molecules with that speed also increases. And that is when we look at under the curve under the graph, the when you look at when you take the area under each of these curve, you see that the one of 2273 will have the largest, meaning that at higher temperature, you have more molecules that will be able to move at that speed. So as just like I explained, as the average temperature increases, the speed increases. And of course, the average kinetic energy is related to the temperature. Now, if you remember well, when I started, I talked about the fact that the gas, when you put them in a whatever the identity is, if you put them together, they really mix well. Why is that so important? It's because they only interact when they collide. And that collision is usually very, very short, just in few seconds. It's just like touch and go, touch and go. So they don't really have so much time for interaction. Therefore, their chemical properties don't usually matter. So what we usually describe them about, what we use to describe them, you will see they are more of their physical properties because there isn't so much interaction between them for us to now be able to have talk about their chemical properties. So the next thing we're going to look at, we'll start looking at the different gas laws. There are some, most of them we are already familiar with, but we'll just try to remind ourselves and take some examples. The first one we'll be looking at is Boyle's law. What does Boyle's law tell us? The volume of a given mass of gas is inversely proportional to the volume, to the pressure at constant temperature. And this is being illustrated in this in the diagram here. When you have a pressure of 780 torr, you can see that the volume is 20 mil. At higher volume, it means you have low pressure. When you now increase the pressure, we are exerting a force. You are going to compress and reduce the volume. You can see that at a higher pressure, the volume is reduced. So P is inversely proportional to V. That is our Boyle's law. So our PV equals to a constant. That's if we remove the constants of proportionality. And then if we have initial and final conditions, we will have P1 V1 equals to PV2 P2 V2 equals to P3 V3 and so on and so forth. And this is a basic explanation of what happens with the Boyle's law. If at 1 atmosphere, that's at a low pressure, you can see that the gases are not compressed. You see, they can move, they are still free to move about. They have larger volumes. But when you now apply pressure, you see that the volume is compressed. They are, clustered together.
You buy this from your house or you bought it?
And then we also have the Charles law. The Charles law talks about the relationship between volume and temperature at constant pressure. So Charles law states that the volume of a gas is directly related to its temperature at constant pressure. So in the case of gas law, as we increase the temperature, the volume also increases. And this is illustrated in the diagrams we have over here. So V is directly proportional to T. So if you remove the proportionality sign and introduce the constant, we have V1 all over T1 equals to V2 all over T2 equals to V3 over T3, and so on and so forth. So a simple explanation to why Charles law is, to why we have the Charles law is that, just like we have mentioned earlier, when you increase the temperature, you are giving them more energy. The average kinetic energy increases. And when that is so, they are able to move about. The more far apart they move, the more the volume they occupy. So that is why you can see here, when you have the balloon of gases in the ice water, and then when you now put the same one in boiling water, you can see the difference in the volume of the balloon. So at higher temperature, they get more energy and they are able to move about. And of course, the more you free them to move, the more volume they'll be occupying. Now let's take some examples. So we have a sample of carbon monoxide gas occupies 3.2 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? If the pressure remains constant, that is already giving us an insight that we are going to use the Charles law. So V1 T1 equals to V2 T2. We have V1 at 3.2. We have T1 at 125 degrees Celsius. Don't forget, we need to convert to Kelvin by adding 273, and that's what gave us this 398.15. Then the V2, we are given 1.54. We are looking for T2. So we just rearrange the equation, put in all the variables, and get our answer as 192 Kelvin. We have another question here. A gas occupies 100 ml at 150 kilopascal. Find its volume at 200 kilopascal. What law are we going to use here? We have the volume, we have pressure at initial pressure, we have the final pressure. So it means we are going to apply Boyle's law. P1 V1 equals to P2 V2, because the temperature wasn't mentioned, or it was kept constant. And then when we put in all the variables, we get our V2 to be 75 mil. The next thing we are going to do is that we are going to combine this gas law, this Boyle's law and Charles law. We can combine them to have the general gas law, or what we call the combined gas law. So if we have Boyle's law, V inversely proportional to P, and then we have the Charles law, V directly proportional to T, and then we now combine them. V directly proportional to T, inversely proportional to P, and then when we remove the constants of proportionality and we introduce a constant, we have PV over T equals to K. So if you have a set of conditions, just like we did for Charles law and Boyle's law, where you have an initial and a final, you have a set of conditions, one at the initial and then the other at the final stage, then we can also apply this P1 V1 T1 equals to P2 V2 all over T2, or P initial V initial T initial equals to P final V final T final. So you can, in as much as you have your pressure in the same units, that's the only thing you should check out for when you are doing this kind of calculation. If you are giving one pressure in torr and you are giving the other one in millimeter mercury, make sure they have the same. You must convert them, let them have the same units. If the volume as well, make sure the two, both the initial and the final, they have the same units. And then temperature, compulsorily, temperature must be in Kelvin. If you are given in degrees Celsius, you make sure you convert to Kelvin. And then we have an example here. We have a sample of gas having a volume of 2.5 liters at a temperature of 30 degrees Celsius and a pressure of 1.8 atmosphere. What volume in liters will the sample have if the pressure is increased to 3 atmosphere and the temperature is increased to 100 degrees Celsius? So we can see here that we have all the three variables are there. There is nothing constant. We have the volume, we have the temperature, and then we have the atmosphere. So that tells us that we are going to use the general gas law or the combined gas law. So we just make sure you convert the temperature to Kelvin. So we have initial pressure, final pressure. We have initial volume, but we don't have the final volume. That's what we are looking for. We have the initial temperature and then the final temperature. So we put that into the equation, and we have our value to be 1.85 liters. We have another example here. A gas has a volume of 4.2 liters and 110 kilopascal. If the temperature is constant, find the pressure of the gas when the volume changes to 11.3. We have been given a clue if the temperature is constant. So what are we going to do? We apply the same general gas equation here to get our volume, to get our pressure. So these are examples. They are very simple examples, things we can work by ourselves. We have the temperature and volume of the gas at 150 degrees, 300 EMQ. Given the final volume at 100 EMQ, we have to find the final temperature in degrees Celsius. Now, here, we are asked to look for the final pressure in degrees Celsius. So watch out for this kind of question, because in the exam, you find both the value in Kelvin and degrees Celsius. But the examiner has told you that you find your final temperature in degrees Celsius. Even though in the calculation you are going to convert to degrees Celsius, to Kelvin, to get your final volume, temperature, which is 141 Kelvin. But the examiner wants you to get your answer in degrees Celsius. So that means you will subtract 273 Kelvin from here to get your final answer as minus 132 degrees Celsius. If you come across this kind of question, you see the answer for both 141 Kelvin and minus 132 degrees Celsius. A student who is not careful enough will just go and cycle 141 Kelvin because you're already used to the fact that you are working in Kelvin. But make sure you read questions very well. Read in between the lines. Know what the examiner has asked you to do. Now, the next one we are going to be doing or going through is the Avogadro's law. The Avogadro's law states that equal volume of gases at the same temperature and pressure contain the same number of molecules. So it means that at constant temperature and pressure, the volume of gas is directly proportional to the number of moles. And that is what gave us this V, we should have V directly proportional to N. And then when we introduce the constants, we have V equals to Kn. And then we can do our usual V1 over N1 equals to V2 over N2, and so on and so forth. So this is a plot of the showing the Avogadro's law. As we increase the number of moles, the volume increases. And we have an example here. Ammonia bonds in oxygen to form nitric oxide and water vapor. How many volumes of NO are obtained from one volume of ammonia at the same temperature and pressure? This is trying to test the Avogadro's number. So the first thing we do is to write the equation of reaction. We can see from here the number of moles of ammonia and the number of moles of NO, they are the same. So 4 moles of ammonia requires would burn in oxygen to form 4 moles of NO. So it means 1 mole of ammonia will also burn in oxygen to give the same 1 mole of NO from the stoichiometry. 4:4, 1:1. So at constant temperature and pressure, we expect that the mole will be synonymous to the volume. That's what Avogadro told us. So 1 mole of ammonia, which will burn to give 1 mole of NO, it means that 1 mole of ammonia, 1 volume of ammonia will also burn in oxygen to give 1 volume of NO. So that's the answer. Very straightforward and simple as that. Once you can write the equation of reaction, balance it, then you are good to go with Avogadro's law. And this is an illustration of what happens with the Avogadro's law. When at the initial stage, the pressure, the atmospheric pressure and the pressure of the gas is the same. But now when you now add more gas, you increase the number of moles of gas. The gases in there, they will now begin to collide. You are increasing the collision. And then when that happens, they exert pressure. So it means that the pressure of the gas will now be greater than that atmospheric pressure. So to now balance it again, you have to let them go, increase the volume so that they can space out, and then the atmospheric gas now equals back to the pressure of the gas. So that is just trying to illustrate to us the Avogadro's law. Then the next one is the ideal gas law. So the ideal gas law, we are going to combine the Avogadro's law with that combined law that we did earlier. So we know, so that means we are combining 3 laws: the Boyle's law, the Charles law, and then the Avogadro's law. So we are combining V inversely proportional to P, V directly proportional to T, and V directly proportional to N. Okay? So if we bring all that together, we have V, it will be directly proportional to N and T, and inversely proportional to P. That's V proportionality NT divided by P. N and T will be the numerator, P will be the denominator. And then when we now introduce our constant, we remove that proportionality sign, introduce our constant, we have V equals to constant multiplied by NT over P. That our constant is what we call the gas constant, R. That is where in the history of R, we hear about the gas constant. That is where we got that R from. It is when we were combining the 3 gas laws, that constant there is what we call the gas constant, R. So if we now cross multiply, we have Vp equals to nRT. Okay? PV equals to nRT. So that is our ideal gas law. So we have the standard conditions at 0 degrees Celsius, and 1 atmosphere. How do we now get, and we already mentioned earlier that at standard temperature and pressure, that is 0 degrees Celsius and 1 atmosphere, 1 mole of a gas will occupy 22.4 liters. And we have PV equals to nRT. What we are trying to look for is the numerical value of R. If our P is 1 atmosphere, our V is 22.4 liters, our T, the temperature, 0 degrees Celsius, that is converting to Kelvin. What is the R? And of course, our N is 1 mole. So if you put all these variables, what is the value of our R? R equals to PV over NT. Pressure, all these are under standard conditions. So we put their values as standard conditions. P, 1 atmosphere, volume, 22.4, N, 1 mole, and T, 0 degrees Celsius, 273 Kelvin. So when we press our calculator, we have our R to be 0.082057 liter atmosphere per mole Kelvin. So that is the numerical value of R. So when we are given that R in calculations as a constant, this is how we derived the R, just to let you know. That is where R came from, the value of that R. So these are things to bear in mind. Just to reiterate what we have said, our temperature must be in Kelvin, pressure is force per unit area, and then we have our volume. We could have it in different units. I've mentioned 2 units already earlier. I've said 20 dm cube and liter. 1 dm cube equals to 1 liter. And then 1 liter is the same thing as 1000 cm cube or 1000 mil, which is the same thing as 10 raised to the power minus 3 meter cube. So this is also trying to give us the different units, that the volume, the different units of volume. So if we have a problem involving a set of initial and final conditions, and all 3 variables are there, pressure, volume, and temperature, you use combined gas law. But if the problem gives information for one set of conditions, if you have the volume, the pressure, the temperature, and the number of moles, but they are not in 2 sets, you don't have it in initial and final, then you know that you use the ideal gas law. Now, we could also have our calculation. There are other parameters that we can also calculate using our gas equation. You know that density equals to mass over volume. Where M is the mass of the gas, and then we know that M is the molar mass of the gas, and we know that the molar mass of a gas is equal to number of moles of gas is equal to mass over molar mass. So our molar mass now becomes dRT over P. Now, before I go further, how did we get this? You know that our PV, that's one thing that is supposed to be here, sorry. You know, our PV equals to nRT. So our V, if our PV equals to nRT, then our V equals to our PV equals to nRT. So our V will be equal to, if PV equals to nRT, then our V will be equal to nRT divided by P. That is what we did here. So we replace the V with nRT over V, or nR over T. That was what we did here. Okay. So, and then we can make molar mass the subject of the formula. Molar mass becomes dRT all over P from this first equation, where D is the density of the gas in gram per liter. Just a minute. I want to quickly illustrate this properly. Let me see if I can get the other side. That's the
If I told you that I'm going outside, I cannot hear what you are saying.
I want to show you properly how we got that density so that you understand what I'm saying. You know, our PV equals to nRT. So, and then N is the number of moles. And we all know from our basic chemistry, the number of moles equals to mass over molar mass. So we replace that N with mass over molar mass, RT. Okay? And then we know that our density equals to mass over volume. So if, our density equals to mass over volume. If we make mass the subject of the formula, here we will have it as PM over RT. So that is how we got this D equals to PM over RT. I'm just trying to show us how we got, how we arrived at that formula. We have PV equals to nRT. N is being replaced, number of moles is the same thing as mass over molar mass. So PV now becomes, instead of N, we write M over M, mass over molar mass, RT. And then already we know that density equals to mass over volume. So if we substitute that, we now get PM all over RT. So I hope it is clear now. I'm just trying to break it down in a simpler way for us to understand how we got that formula. Let me go back to my original slide. This was just by the way. So, what is this is an example. What is the volume in liters occupied by 49.8 grams of HCl at STP? So here we can see that there are no initial conditions, no final conditions. So that tells us we are going to use the ideal gas equation, PV equals to nRT. We are given the temperature at STP, that's 0 degrees Celsius, we convert to Kelvin. The pressure, STP, 1 atmosphere. Then the volume will now be V equals to nRT over P. Our N, number of moles, will be the mass over molar mass. That's the mass of the HCl, 49.8, divided by the molar mass of HCl, 36.45. So when we now substitute all of that, we get 30.6 liters. Or we first of all convert that mass of HCl to mole by dividing by the molar mass. That will give us 1.37 mole. Then we now put in all those variables in V equals to nRT over P. Then we get our volume as 30.6 mole, 30.6 liters. Sorry. We have another example here. Argon is an inert gas used in light bulbs to retard the vaporization of the filament. A certain light bulb containing argon at 120 atmosphere and 18 degrees Celsius is heated to 85 degrees Celsius at constant volume. What is the final pressure of argon in the light bulb? So you write out all the parameters you are given. You are given 1.2 atmosphere as the volume. We are given 18 degrees Celsius as the temperature. We'll convert that to Kelvin by adding 273. And we are given a final temperature, 85 degrees Celsius, convert that to Kelvin by adding 273. And we are asked to find the final pressure. So it means that we don't even need to go far. What law are we going to use here? What are the variables? What are the constants? It means pressure and temperature are the variables. Pressure and temperature are the variables. And then we go for Boyle's law. P1 over T1 equals to P2 over T2. So depending on the question, you need to read and see, okay, what are the variables? What is kept constant? Then you will be able to know which of the laws you apply to solve such a problem. So I have sample problems here that I will send to you as practice. We have, just like we mentioned, we can use the ideal gas to find other, to solve other problems in density of gas. We can use it to solve molar mass. From what we saw in the other equation, we can solve molar mass. Then if we have a balanced chemical equation, we can also use it to solve it. So that is all about the Boyle's law, Charles' law, Avogadro's law, the combined gas law, and then the ideal gas law. So the next thing we'll be looking at the next law we'll be looking at is the Dalton's law of partial pressure. So mixture, if you have a mixture of gases, Dalton's law states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. Meaning that if you have three mixture of gases, A, B, C, the total pressure gas A gas B, and gas C we exert will be the sum of the individual pressure of the gas. Say, for example, gas A exerts 10 atmosphere, gas B exerts 8 atmosphere, and gas C exerts 6 atmosphere. The total pressure, it will just be summing all those gases together. And in other words, if those gases, if they were present by themselves, present alone, it is still that same gas, that pressure they will exert if they're in a mixture, that they will exert if they were alone in the sample container. That is what Dalton's law. That is what Dalton's law tells us. Dalton's law of partial pressure tells us. So I can see some, let me use the remaining few minutes to ask if you have questions on what we have done so far. Do we have any questions? I'll send practice questions to your, we need to get in touch with class reps so that we can give you more practice questions to be able to lay your hands upon. But I want to believe so far what we have done is not something totally strange. There are things we must have come across when we were maybe doing preparing for SSC, JAMB, and all. So if we have any question, we can ask. Otherwise, I'll stop here today, and then on Wednesday, we shall continue with the class. So we still continue with this Dalton's law of partial pressure. We talk about the mole fraction, Graham's law of diffusion. So we'll stop here for today and continue from here on Wednesday. In the absence of any question, I'll leave you to enjoy the rest of the day, and I'll see you on Wednesday. Oh, okay. Somebody is asking if I can explain the density formula again. Okay, let's go back to the density formula. Just a minute. Let me use the other slide. Yes, Damilare. Damilare, you can ask your question. Are you the one asking about the density, the formula of density? Damilare, I've unmuted you. You can ask your question. Just give me a minute. Let me read. Yes, Damilare. So the density calculation again, we have PV equals to nRT. We have N, which is mass over molar mass. That's what is replacing that N. PV equals to small m over big M, mass over molar mass, replacing N, and then RT. And then on this, we could also have this to be equal to PMV divided by RT equals to MRT. That's if we divide both sides, if we cross multiply. So PMV RT will equal to MRT. So dividing both sides, dividing this by RT, we can then go to this formula D equals to M over V, mass over volume, and then we now substitute for volume, which will now be PM over RT. So that is how we got that density. I hope it is clear now. So